Howdy folks, in this video we're going to talk about how do we calculate a confidence interval for population means, and this is the one sample case. Okay, alright, so we've had previous discussion on confidence intervals, and we know from previous discussions that confidence intervals are based on the central limit theorem. But the central limit theorem for means states that if the sample size is large enough, the sample distribution becomes approximately normal, with the mean equaling the population mean, and the standard deviation of the sampling distribution is sigma, the population standard deviation, divided by the square root of n. However, we got a little bit of a problem here, folks. In most applications, in most scenarios, the population standard deviation is unknown. Okay, so most of the time we do not know the population standard deviation, which is that sigma symbol. So a reasonable thing to do would be to use instead a sample standard deviation, right? Because remember, this whole thing about confidence intervals, we're collecting a sample and we're using that to make an estimation of a population value. So why don't we use the sample value? And that's exactly what we're going to do. We're going to use the sample standard deviation S, but there's a little bit of an issue. Once we decide to use the sample standard deviation S, we can no longer use the Z distribution, which is our normal tables and our normal calculator. Instead, we're going to have to use something called the T distribution. And so give me a few minutes. I'm going to explain what is the T distribution. All right. So the T distribution is actually, it's a family of these bell-shaped curves, right? So we know that the normal distribution is a bell-shaped curve, right? And by bell-shaped curve, I mean something like this. But it turns out that the T distribution has fatter tails. What I mean by that is that as the tails approach the horizontal axis, there's a little bit more space between them and the horizontal axis, okay? Also, a very key metric or a very key thing that we use to describe a T distribution is something called degrees of freedom. So degrees of freedom, mathematically speaking, is the number of basically dependent variables. But anyways, for you guys, all we need to know is that our degrees of freedom will be n minus 1. So to get your degrees of freedom, it's going to be n minus 1. Okay? Excuse me, I misspoke. The degrees of freedom is the number of independent directions that we can go. But yeah, so n minus 1. So your degrees of freedom will be n minus 1. So it turns out that as the degrees of freedom increases, as we get a larger and larger sample size, this T distribution with these fatter tails, and it becomes closer and closer to looking like the normal distribution. This means that the center stays the same as our degrees of freedom increases, which means our sample size is increasing. The center stays the same, but the distribution becomes tighter, becomes skinnier, more narrow. Okay? So that's the T distribution. And so we're going to do things similar to what we've done in previous sections related to the Z distribution, but we're going to use it with T. And anytime we work with T, we have to specify, once again, the degrees of freedom, which is one less than your sample size. Okay. The confidence interval for means, we call this the T interval for one sample. If the conditions are met, then the confidence interval is found by, we've seen this before, adding and subtracting the margin of error to, this time we're going to be adding and subtracting the margin of error to the sample mean. Remember, we're trying to find a confidence interval for means. So you take X bar, add and subtract your margin of error. Okay? All right, so what is the margin of error? Okay, so your margin of error turns out that it is your critical t-score. I'll explain all this in a second. It has this symbol T star with a subscript of n minus 1. So T star, we know star means critical. The n minus 1 is telling you the degrees of freedom. And then we multiply that. Listen, this is coming straight from the central limit theorem. We multiply it by the standard deviation, in our case the sample standard deviation, divided by the square root of n. Okay? So as I said, X bar is your sample mean. That T star, that is your critical t-score. I'll show you how to calculate that. S is your sample standard deviation, and N is your sample size. Okay? It goes without saying. Hey, remember, confidence intervals estimate population values. We are estimating an unknown population value. Okay? Confidence intervals do not say anything about individual data values. They only estimate a population value. Just keep that in mind. Okay, before we get into some actual calculations here, let's go over the conditions necessary. So these conditions are, once again, straight from the central limit theorem. So we need an independence assumption. We need to assume that our data values are independent. How do we do that? You've seen this before. We have a randomization condition. If we conducted a random sample, or these samples were, collected randomly, then we have a randomization condition which will ensure independence. Also, to help out independence, we got to make sure that we sample less than 10% of the population. Okay, so that randomization condition combined with the 10% condition satisfies independence. And the last thing, if you notice, for central limit theorem for means is that we needed to make sure that our sample size was large enough. And so what we're saying here is that for t intervals, and anytime we're working with the t distribution in general, we need to have this nearly normal condition. What that means is that this t distribution works better whenever the population that we're dealing with is close to being normal, okay? Especially for small sample sizes, okay? So let's say for sample sizes less than 30, we need to make sure that the data comes from a normal population, okay? And what that means is we're looking at unimodal and symmetric, right? We got to avoid those outliers and those extremely skewed data. So what we often do in this case for small sample size is we look at the histogram. Okay, and I'll show you how to do that. We've done that before. So we're going to look at the histogram. That's what we really need to pay attention to for sample size less than 30. In general, if our sample size is larger than 30, we are good to go. All right, large enough sample size is usually bigger than 30, unless our data is extremely skewed. If our data is extremely skewed, then we're going to need a larger sample size there. Okay, so those are the conditions. The independence assumption comes from randomization and less than 10% of the population being sampled, and then we have to be nearly normal. So that means if our sample size is less than 30, let's check the histogram and see if the histogram is unimodal and symmetric, bell-shaped curve. And then if our sample size is larger than 30, we're good to go. Okay, so I hope that's clear. Those are the conditions necessary for a t interval. All right. Finally, let's get into it. For example, in a simple random sample of 400 high school seniors, they gained an average of 9 points in their second attempt of the SAT math exam with a standard deviation of 40 points. So the students are taking the SAT a second time. We're saying that their average increase of score in that second attempt is 9 points with a standard deviation of 40 points. Assume the change in score has a normal distribution. Okay, check the conditions necessary to perform a 95% confidence interval for the population mean change in score for all high school seniors. Okay, so let's check the conditions. So our independence condition needs to be checked via, did we take a random sample, and did we sample less than 10%? So let's take these one at a time. All right, random sample. Well, they tell us we performed a simple random sample. So yes, we have the randomization condition met. Less than 10%. We're sampling 400 high school students. Certainly, there's a lot more than 400 high school students. So yes, we are sampling less than 10% of the population. Therefore, independence, we can assume that. All right. The next condition is the nearly normal condition. Okay, well, there's two ways we can look at that. Well, first of all, they tell us that assume that the score comes from a normal distribution. So that's already satisfied. And then I'm going to give this another check because look at our sample size. Our sample size is 400. 400 is big enough, is large enough, let's say. Okay, so even if they did not tell us that we had a normal distribution, we still would be okay because our sample size is really large, relatively speaking. 400, way bigger than 30. Okay? So with all that being said, all the conditions are met in order to find the confidence interval. In part B, they want us to do exactly that. Find the confidence interval. All right? So I'm going to do, I'm just going to remind myself what the formula for the confidence interval is. It is x bar plus or minus our critical t-score times the sample standard deviation over the square root of n, okay? All right, I'm just going to copy these down for my benefit here. So we know that x bar, the sample mean, was 9, and the sample standard deviation was 40. So we know x bar was 9, we know that s was 40. We know our sample size was 400. They sampled 400 seniors. Okay, and we want to be 95% confident. So let me show you how to calculate T star, our critical t-score. And we're going to do it using technology, folks. We're getting fancy. All right, so the process of finding T star is very similar to what we've seen in previous videos. So I'll show you here. So based off of everything we said, we know that the T distribution is approximately normal. These are t-scores. So T is centered at 0. It's very similar to the normal distribution. And once again, we're going to have two T values, right? Two T criticals. The only difference is that one is negative and one is positive, okay? And then we know that we always use the positive version. So what I'm going to do is I'm going to focus on, we need to get that area in that tail, right? So how do we get that? So if you guys remember from before, when we're 95% confident, that means that's the area in between the two, in this case, t-scores. So that is 0.95, which means the area in the left and right tail will be half of the unshaded area. So this red area is going to be 0.05 divided by 2, which is 0.025. And for that same reason, we're going to have a 0.025 in that right tail there, okay? All right, so to get to find our t-score, this is what I'm going to do. Let's go to StatCrunch, okay? We're not going to even mess with the tables. Let's go straight to StatCrunch. And then under Stat, we are going to go to Calculators, and we're going to go to T. We're going to go to T, all right? Okay. So I believe you guys have seen this trick before, but what we're going to do is, first of all, notice DF. DF is for degrees of freedom. I'm hoping you guys can see that, okay? All right, so what I'm going to do, our degrees of freedom was our sample size was 400. So 400 minus 1 means our degrees of freedom is 399, okay? All right, and then now, what we need to do is, we do not know what the t-score is, but we know the area to the left of the t-score that we want was that 0.025. So this is going to be 0.025 that we type into here. Okay, we click compute, and boom, that is our t-score. It is a negative 1.96. Notice how close that t-score is to the critical value for the normal distribution, which was also negative 1.96. That's because that degrees of freedom is really, really large, so we're really, really close to being a normal distribution. But anyways, negative 1.96 is what we'll put here, which indicates the positive version is the critical t-score that we're going to use. All right, here we go. All right, so then we do, let's go different color. Our X bar is 40, excuse me, no, 9. Sample mean is 9, plus or minus, we're going to calculate this margin of error. It's going to be 1.96 times S, which is 40, divided by the square root of 400. Okay, so I'm going to go to my calculator. So I'm going to calculate that margin of error. So we said that was 1.96 times 40 divided by the square root of n, which was 400. So 3.92 is what we got there. So the margin of error is 3.92. Now we're going to subtract to get the lower end of our interval. We're going to add to get the upper end of our interval. Okay? So we're going to take, 9 minus 3.92, which is 5.08. Make sure you guys can see that. Up to 9 plus 3.92 is going to give us 12.92. All right, to verify that, 9 plus 3.92, 12.92. All right? So that is our 95% confidence interval. I don't think that was terrible. But if you want an even quicker way of doing this, let me show you how to do this in StatCrunch with some technology. All right? So what you're going to do is, let me see, let's zoom this out a little bit. Let's close this out. Okay, we're going to go to Stat. And close up that calculator menu. We're going to go to T-Stats. Okay, and then we're going to do one sample. And then this is going to be with summary. We have the summary statistics. Give me a couple minutes. I'll show you how to do this with data. All right, our sample means, just type in the information that we calculated, right? Our sample mean was 9. Our sample standard deviation was 40. And our sample size was 400. Okay. What are we performing? We'll talk about hypothesis tests later on in this semester, but right now we're doing a confidence interval for the mean with a confidence level of 95%, 0.95. All right. Let's go to compute in your top right-hand corner here, or whatever you may see in your computer. And look at that, folks. We are very close to what we calculated by hand, 5.07 to 12.93. Slight differences because we rounded. This is a more exact answer. But I hope you see it's the very, very similar answer to what we got. And it's a lot quicker. I recommend doing it this way. Do it this way. All right. So that is our confidence interval. Let's interpret it really quickly. Write an interpretation of your confidence interval. Hopefully you guys know the script by now. It goes, we are 95% confident that the population mean score change is between the two values that we calculated. Let's go with the ones that we did by hand. 5.08 to 12.92. All right. There we go, folks. That is your interpretation. I just want to piggyback on this. We talked about this in previous videos, but let's do it again. What does it mean to be 95% confident? Okay. 95% confidence means that, let's do it this way. 95% confident means that 95% of all confidence intervals, goodness gracious, I can't write. So 95% of all confidence intervals generated from sampling the population will include the true population mean. So what are we saying here? We're saying, first of all, we're letting them know that, listen, every time we take a sample, we're going to get a different confidence interval, okay? But when we say we're 95% confident, we're saying that we believe this method, the method itself of how we did this, to be correct 95% of the time. That means that if I take all the possible samples from a population and I calculate all these different confidence intervals, 95% of all those confidence intervals we created will contain the actual population mean. So the 95% confidence is a measurement of the method that you perform, not necessarily the the numbers that you get. Please do not say there is a 95% chance that the mean is between blah, blah, blah. Do not say that. Let's put a big X, red X on that. Do not say there's a 95% chance that the population mean lies in that interval. No, do not say that. Okay? All right, moving along here. Another example, we have in 1998, as an advertising campaign, the Nabisco Company announced a 1,000 chips challenge, claiming that every 18-ounce bag of their Chips Ahoy cookies contain at least 1,000 chocolate chips. I'm hungry. Dedicated statistics students at the Air Force Academy purchased some randomly selected bags of cookies and counted the chocolate chips. The data that they collected from those bags of cookies has been copied to StatCrunch for you, okay? So they had data values. All right, first thing, part A, check the condition necessary for a 95% confidence interval, okay? So can we perform a 95% confidence interval? All right, what are the conditions? Remember that independence assumption. Okay, the independence assumption comes down to two conditions. Did we randomly sample the population? I'm sorry, guys, with my hands, right? This is terrible. Let's do this. Randomization. Okay, and did we sample less than 10% of the population? All right, so, well, they tell us we randomly selected bags of cookies. We are good to go. And the 10% condition, if you look at the data, I think there's only like 15 data values. So they only grabbed 15 bags of cookies, excuse me. So certainly we sampled less than 10%, okay? And so that means our independence assumption is satisfied. Listen, guys, even if we didn't do like a random sample there, we could still kind of assume randomization because we're, due to just inherent variability whenever you're filling a bag of cookies, right? So even if they didn't say that they collected these randomly, we could still reasonably assume that there is a bit of randomness going on with those bag of cookies, okay? All right, and then the next condition is that, are we nearly normal? Okay, so let's actually look at the data values here. Let's do that. So let me go to StatCrunch. Let me close this out. And here are the data values here. So there's 14 data values. So that means that they grab 14 bags of cookies. And then you're seeing the number of chocolate chips for the 14 bags of cookies. Okay, because they don't say anything about this being a normal distribution, and because we have certainly less than 30 data values, we need to check the histogram. So let's remind ourselves on how we do that. So we go to, I believe, graph. Yes, we go to graph, we go to histogram. Okay, select your columns. We want to do this for variable 1. Okay, that's where all our data values are. And then nothing else we really have to worry about. Okay, we just want to get an idea of what the histogram looks like. So I'm going to go ahead and go to compute. And there's our histogram. And roughly speaking, that's pretty symmetric and unimodal, okay? I mean, we don't need anything super symmetric and unimodal. We just don't need anything that's an outlier or extreme or really skewed, right? So there's a little bit of skewness here, but overall, this is pretty symmetric and uniform, okay? So that's how you find your histogram. So let me go back here. So what we can say here is that the histogram appears symmetric and unimodal. So therefore, folks, we can go ahead and say, yeah, we have satisfied the normal condition. So all the conditions are met. If you're less than 30, folks, just check the histogram. Make sure there's no crazy outliers or like really extreme skewness. Okay, find the sample mean and the sample standard deviation of the data set. Here, I just want to remind you guys on how to find those values. Okay, so how do we do that? We're back in StatCrunch. We're going to go back to Stat. we're going to go to summary statistics, and we're going to let them know that we're going to be selecting these from columns. Okay, the column that we want is variable 1. Okay, and then we can choose what statistics we want. N, mean, variance, standard deviation, standard error, median. I'm going to just unselect some of these. Feel free to keep them in if you want to. All right, that's all we know. All we need is the mean and the standard deviation. Okay, so we're going to come here. We're going to go to compute. There we go. The mean to, hope you guys can see that. The mean to 2 decimal places is 1249.93. Let's write that down. So X bar is 1249.93. And the standard deviation is 94.23. And S, the sample standard deviation, is 94.23. Okay? So if a question asks you about how to find the mean standard deviation, that's how you do it. All right, lastly, calculate and interpret a 95% confidence interval. Now, we could go through and do this by hand, but we're not doing that, folks. We're going to use technology. So this is what we do. Let's go back to StatCrunch. Let me close out of this. I'm in my data set. We've seen this before. We hit Stat. We click on T-Stats. We're going to do this with data this time, with data. The column that we're going to, that houses our data set is under variable 1. And then under perform, we're going to select confidence interval. We want to be 95% confident. That's all we need. Easy peasy. Go to compute. And there is our confidence interval. The L limit is your lower bound. The U limit is your upper bound. DF is your degrees of freedom. Remember, we had 14 data values, so 14 minus 1 is 13. So there we go. So 1195.52. If we go to 2 decimal places, up to 1304.34. Okay. So what does this mean? This means that we are 95% confident that the population mean number of chocolate chips is between 1195.52 and 1304.34. Okay? All right, lastly, what does this confidence interval suggest about Nabisco's claim? Okay, what did Nabisco claim? They said, and I quote, "Every bag of cookies contains at least 1,000 chocolate chips." Okay, well, look at our confidence interval. We're saying that we are 95% confident that the number of chocolate chips in a bag, the average number of chocolate chips in the bag is between 1195 and 1304. So that entire confidence interval is more than the 1,000 chips that Nabisco is claiming. So what does this confidence interval suggest about Nabisco's claim? Our confidence interval seems to validate Nabisco's claim. So basically, we're saying we're pretty confident that what they're saying is true, right? Validate means, right, is true. So our confidence interval seems to validate Nabisco's claim. So they were correct in what they were saying. There was no false advertising there. All right. If our confidence interval had went from maybe 900 to 1,200, then we can get a little nervous because it is possible, extremely possible actually, that they would have less than 1,000 chips there, right? But based off of this, based off our confidence interval, since the lower bound is higher than 1,000 and the upper bound certainly higher than 1,000, we are pretty confident and saying that Nabisco's claim is true. Hope that makes sense. All right, last one, guys. I appreciate y'all hanging in there. An English professor is attempting to estimate the mean number of books that the student body reads during their time in college. To gather data about this, an exit survey will be conducted with seniors. The estimate is to have a margin of error of 4 books with 95% confidence. The professor will assume the standard deviation is 10 books. How many students should take the survey? So basically, this question is asking, what's the sample size needed? Okay, what's the sample size needed in order to conduct, to calculate this confidence interval to the specifications that the professor wants? Okay, well, if you go back earlier, we talked about the margin of error. And we said the margin of error was our critical t-score, right? Our critical t-score times, what do we say? The sample standard deviation divided by the square root of n, okay? And so what we need to do, and we've done this before in a previous video, is we need to solve for n. We need to solve for n. So what I'm going to do is I'm going to go through the algebra real quick. Feel free to skip ahead to get just to the final answer, but this is what we're going to do. First of all, I'm going to divide through by my critical t-score. All right, we do that. We are left with the margin of error divided by the critical t-score, the degrees of freedom n minus 1, and then that's going to equal our sample standard deviation divided by the square root of n. Okay? All right, next thing what I'm going to do is I'm going to invert fractions on both sides. It's legal. It'll work, right? So if I flip the left side, yeah, just do this. So then if I flip my right fraction, right, if I invert my left fraction, excuse me, then I have to invert my right side fraction. Okay? That's legal. I mean, if basically what I'm doing is multiplying both sides by the square root of n, and then just moving things over. Trust me, it's legal. Multiply both sides by my sample standard deviation. Hope you guys can see this, ME. And then we are almost there. I'm going to put that S in the numerator. And then the last step is to square both sides, okay? All right, so I'm going to write the final answer up here. So the sample size needed, here is your formula. This is all you need to know, y'all. N equals, that's a weird color. It is your critical t-score times your sample standard deviation divided by your margin of error, and then that entire fraction needs to be squared, okay? That's our formula to figure out the sample size needed, okay? All right, now all that we need to do, let's give ourselves some space here. All we need to do now is fill in the values with what we have from the question itself, right? So, n equals our critical t-score, okay? We need to be 95% confident. I know you guys are so sick of drawing this, but it's really the crux of these chapters. We have our t-scores right down the middle. T is equal to 0. We know that there are 2 critical t-scores. One's negative, one's positive, and we know the area in the middle is 95%. And so that means the area in this left tail is 0.05 divided by 2, which is 0.025. And for that reason, the area in this tail is a 0.025. So what we're going to do is we're going to go to our, and we need degrees of freedom. All right, so we're in a bit of a pickle here because to find the t-score, we need degrees of freedom. Degrees of freedom is based off of n, our sample size, which is precisely the thing that we are trying to calculate. So this is the trick on how to figure out the n needed for your t-score. What you do, so let's actually write this down. To find the n for your degrees of freedom, this is what you do. Assume that you're working with the z distribution, right? So what that means is that if we need to be 95% confident, right, that means that, remember the 68, 95, 99.7 rule? We're going to apply that. So that means that we need to be approximately 2 standard deviations within the mean, right? So we're going to use a z-score of 2 into the n formula. So we're going to use z equals 2 in the n formula. So we're going to replace the t-score with the z-score, and then we're going to use that to calculate our n, okay? All right. So what is that going to look like? So n equals, let me grab a different color, n equals, instead of a t-score, we're going to use a z-score, and since we're 95% confident, that means the z-score has to be 2. All right, so it's going to be 2 times our sample standard deviation. Sample standard deviation is 10 books. 2 times 10 over the margin of error. We want to be estimates that have a margin of error of 4 books. So our margin of error is 4. Okay? And then the formula calls for us to take that and square it. Okay? All right, so I'm going to put this in the calculator. So you can do open parentheses, 2 times 10 divided by 4. The calculator will do the correct orders of operations, square it, and we get 25. So n is equal to 25. So what this means is that our degrees of freedom that we're going to use, okay, so this means that our df, our degrees of freedom, is going to be 25 minus 1, which is 24. And then we're going to redo this n formula, but now we're going to actually plug in the correct t star, okay? So we need to find our t star of 25 minus 1, so degrees of freedom is 24, of, and this is my notation, of 0.025, right? Because remember, that's the area to the left there. All right, so to find that, we're going to go back to StatCrunch. Okay, let's make that a little smaller. Not sure if I can do that. All right, I'm going to go to Stat. We're going to go to Calculators. And we go to T. All right, we're going to go here. We don't care so much for the graph. We just need these values. Our degrees of freedom is 25 minus 1, or 24. And our area to the left is a 0.025. So we calculate that, compute, and we get a negative 2.06. Notice before when we did this, we got a negative 1.96. That's because the degrees of freedom is less in this example. Okay, so negative 2.06. Is our critical t-score, and finally we can say the sample size needed will be, we're going back to this formula. We're going back to this formula. It's going to be our t star. All right, I'm sorry. All right, so when we did the calculator, we got a positive 2.06 or negative 2.06, but remember, we always use the positive version for our actual critical t-score. So we're going to do 2.06 times 10 divided by 4. So that was the t-score times the standard deviation divided by the margin of error squared. And that's going to give us our answer. So we do open parentheses, 2.06 times 10 divided by 4, quantity squared. We get 26.52. 26.52. And the deal with these is that we always want to round up. We always want to be extra careful. So the answer is 27. The professor needs to sample at least 27 students. Alrighty, guys. I hope that clears up how we do confidence intervals, both by hand and also using technology. I highly recommend the technology. I look forward to seeing you guys in the next one.